Hi guys, in today's video we'll try to code two graph neural network methods. The first one is graph convolutional networks and the second one is simplifying graph convolutions. So let's jump right in. First, I would like to acknowledge the help of the authors who made their code publicly available on GitHub. The first one is GCN and the second one is SGC. And these are the BibTeX entries if you're interested in that. I'm installing pytorch-geometric library, which will help us to create the graph and split the data points into test and train samples. Some libraries, and here I'm passing the arguments for stochastic block model dataset to create the synthetic graph. It needs two arguments. First is the number of nodes, which is in a list. Each entry represents how many nodes per class, and the second list is the edge probabilities. We have 5 classes. We must have 5 by 5 array, where it represents the probability of getting an edge between these two classes. I'm preparing some colors for plotting. Here's our dataset. And here is the graph that we will be working on. Use random node split from pytorch-geometric to split the dataset into train, validation, and test. We're using 10% for validation and 10% for testing, and the rest will be used for training. Here is the code for Graph Convolutional Networks. I have another video explaining this code. Please check it out if you haven't already. Basically, we have Graph Convolution class and GCN class. The code for simplifying graph convolutions. We got a SGC class and a function called SGC precompute. But we won't have an idea about this until we read the paper. So let's jump to the paper. Basically, what these guys have done, they removed, here is a nice figure. This is GCN. GCN do feature propagation, linear transformation, and nonlinearity, and at the end, it applies softmax. The authors of this paper suggest just to do k-step feature propagation, then at the end, just do logistic regression. And basically, they have removed the nonlinearity. And this. Now, here is the architecture for SGC. First, it multiplies the adjacency matrix. S here is the adjacency matrix. It multiplies the adjacency matrix for k times. Then it applies that to the feature matrix, and it uses the parameters for the softmax. And down here, they break it down. SGC consists of fixed parameter-free feature extraction smoothing component, x equals s to the power k multiplied by x, followed by a linear logistic regression classifier, y hat equals softmax, x and theta. So this formula here is basically applied by the SGC precompute. We are multiplying the features by the adjacency for a number of times, for a degree. Degree is set by default by the authors to be 2. And this part here, the class SGC, basically it applies the second part of the architecture, which is softmax. It applies the logistic regression part. So it maps the number of features to the number of classes, and it's done that through training. For training GCN and SGC, we have to prepare the data. First, we have to normalize the adjacency matrix. If you go to the GCN paper, you would find a very nice formula about normalizing the adjacency matrix. First, we have to add the identity matrix to the adjacency matrix to create self-loops in the adjacency. Then, we have to create the degree matrix. The degree matrix, we have to take the sum of the connections for each node. Then we have to place that on the diagonal. This is how it. First, we have to force the adjacency matrix to be symmetric, Then we have to add the identity matrix. The degree matrix here is, I couldn't do it in Torch, but because there's always a NumPy solution, I've done it in NumPy. What I'm trying to do is basically I'm trying to take the sum of for each row in the adjacency matrix, which is what I am doing here. Then I'm placing that sum, which is a one-dimensional tensor, into the diagonal of the degree matrix. And I'm doing that using fill diagonal method from NumPy. After that, I'm creating a tensor named D, and I'm taking the inverse of the degree matrix. Then I'm applying the multiplication, which will normalize the adjacency matrix. This step is just to take out the feature matrix and normalize that using functional normalize and labels. Try the model for GCN. We're passing the number of features, the number of hidden units, the number of classes and the dropout, and we're using Adam optimizer. This is an accuracy function that will compute the accuracy for after each training step. Here is the training loop for GCN. I explained that in my other video. And here is the loss, the training loss and validation loss for GCN. For SGC train, we're only passing the number of features and the number of classes. Remember, we're training only the logistic regression, and we're using Adam optimizer for that. Feature propagation, we're multiplying the feature matrix by the adjacency matrix for 2 times. This will basically apply this formula here. Now we started training SGC, setting the gradient to 0, and we're passing the training features. Here I'm using cross entropy loss, and for GCN I'm using NNL loss. I'm trying to stick to the original code as much as I can. So the authors of GCN have used NNL loss, and the authors of SGC have used cross entropy. So I'm trying to stick to the original code. That's why I'm using 2 different losses in this notebook. Calculating the accuracy, then I'm evaluating the model on the validation samples. Here is the training loss for SGC and validation loss for SGC. You can see that it converges faster than GCN. For testing, GCN misclassified 2 samples out of 50. We got 50 samples for testing, and GCN misclassified 2 of these. SGC got the whole testing set accurately, got 100% accuracy. My final remarks in these 2 methods. The result I'm getting here heavily depends on my implementation, the dataset I'm using, and the hyperparameters I'm selecting. My recommendation, if you're trying to use these 2 methods in your work or research, just implement both of these methods and play with the hyperparameters and see which method fits your dataset better. I guess that's it, guys. You can find the notebook I'm working on in the description below. If you find this video helpful, please like and subscribe. It really helps. Thanks for watching. Bye.